So in the last video, we discussed how to measure voltage and current in a simple circuit to validate Ohm's law. There's another important variable which we must not forget, which we have to take into account, because we've seen that the charges propagating through this circuit apply work, or basically they are dissipating work. The question is, where does the energy go, right? Here we have the positive charges would have a higher potential energy than here, right? They travel along this line, along this connection, this conductor, and then they would lower their potential energy. But then the question is, where does the potential energy go? And we know that basically the change in the potential energy is the work, which is either done by the system, which lowers the potential energy, or which is done on the system, which then increases the potential energy. So for example, when we charge a capacitor or move charges from two parallel metal plates, from one plate to another plate, and displace them. We discussed it. So, the concept of power is how much of this energy which is provided, let's say 5 joules, is basically done in a unit time, that's per second. How many joules are we transporting per second? That is the power. The power is, so to say, the average load of the system over time when the energy W, the work W, is dissipated. So, that means the change of the potential energy leads to a work. In this case, it's negative because the system is doing work on the environment, but where is the work done? Yeah, the only element which is exerted to the work is the resistor R, which means, which kind of energy could it be? It's not a motion, it cannot be a kinetic energy, it's not a motor, it's not an engine, it is thermal energy. So resistors get warm, or they can get hot, or they can even be destroyed when you increase the power much above the rated power of the resistors. So depending on the size of the resistor, they can dissipate more or less thermal energy. They can dissipate more or less thermal power. If you have a large resistor, you can imagine this is more rugged, you have a large surface. I'm not talking about the value of the resistor, I'm talking about the physical properties of the resistor. Is it a tiny one or is it a big one? So when you have a big one, then the thermal load is basically distributed over a larger surface, a larger volume, and the system is more relaxed. If you have a small one, a small resistor with the same resistor value, right, you can technically solve this, then that gets really stressed. Good. So, and the work in the system is due to the change of the potential of the charge Q, right? So we calculated this in another video where the positive charge is traveling from a region of higher potential to a region of lower potential. So the potential difference is negative. It loses potential energy, right? We talked about this voltage, final voltage and initial voltage. So from the difference, the delta V is V final minus V initial, right? And if the initial voltage, for example, here is 5 volts or so, and the final voltage is 0, then we have a negative voltage difference. It's a voltage drop. So it travels from a system of higher potential to a system of lower potential. And with Q being positive, W is negative, which means the system is doing work, which is good because that's in accordance with all our formulas we derived so far. Now, let's have a look at these expressions. So we say that W is the potential difference acting on a charge, or it's the charge exerting a potential difference which does the work. And P is W divided by P, so when we divide this by T, both sides, then we get the power P. So P is Q divided by T times delta V. For now, for a constant current, let's say. Usually we would have to look at small changes of Q and small changes of T, right? Which is, yeah. But for now, we assume that we have a constant current flowing in the system. So Q divided by T times V, and now you can see what is Q divided by T. It's charge per time, and that's the current, which is then I times the potential drop, the potential difference delta V. So the power dissipated in a resistor is then I times the potential drop across the resistor. And usually, since the power is dissipated, you can think of this being negative, but you wouldn't have positive power unless you put energy into the system, right? So usually we're just taking here the absolute values. That's good enough. Okay, so let's have a look at the resistor again. You see, we have positive charges here, and we have a voltage drop, and we can count this voltage drop to be positive, right? You can also say that's a voltage drop of minus 5 volts here across this resistor. But yeah, so from a higher potential to a lower potential, and then the charges are losing energy in the resistor. But in fact, it's the electrons, so it's the other way around. But we've seen that this is equivalent. So electrons would then tend to move from a lower potential to a higher potential and applying work. Okay. So that means when we investigate such pairs of voltage and current, we should always add another column, P. So first of all, the unit of power is energy per time, it's joule per second, and that is what we call watts. Okay, so we should, when we do our experiments to verify or validate or verify, basically, we verify validation or verification of the Ohm's law, then we should always take into account the power as well, and that's for free because you are basically presetting voltage, you are measuring the current, and the product of both would then be the actual power for that set of voltage and current for a given resistor. And then you can check whether the power at some point exceeds the power the rated power for the resistor. And if you exceed this a lot, you are going to modify the resistor first, right? Because many resistors are made of thin metal films, or they are made of carbon, mostly graphite, and this graphite gets hot, and then it starts to slowly deteriorate until it even starts glowing, glooming, burning. Okay, so that means in our experimental setup, we preset the volumes in volt, the voltage in volt. We measure, let's say, the current, let's say in ampere, because what we then would get by calculation, we would immediately get P in watts. It's just the multiplication of these two values. And now I want to show you some experimental data which we determined in the lab, really, so that's real measurement data in our electrons. So I did this in last year's lecture. And I want to show you how we can use a spreadsheet program to model the measured data with a linear model. Right? This is the linear model. So we fit a straight line. And if we force the line to run through 0, 0 to the origin of the coordinate system, we would basically simplify the model to this, right? And that is, if you look at this, so we would fit a model. Let's say the model would be, so again, where? Maybe here. So we preset the voltage, but it's easier to understand when we plot the voltage on the y-axis and the current here on the y-axis. In units, of course, right? Let's say volts or ampere or whatever units we have. And then we fit this linear model. This line here would be y is m times x plus b, but b is 0 because it runs through the origin, 0, 0. But we said that the slope of this line is the resistance, because it's how does the voltage change with current. So how does the voltage change with current? Is the resistor a little voltage change with a little current change. But since this is constant here, you see it's a straight line, we just have 1 v divided by I. So, so when we reformulate this, we would have volts is R times I. That's how we started with the Ohm's law. And if you now compare the coefficients, you see that Y now is basically another variable name for the voltage, and X is another variable name for the current. Okay. So now let's do that in a spreadsheet program. So I'm using LibreOffice Calc. So this is LibreOffice Calc. And let's read the data from a file. So, but before we do this, I show you the content of the file, because it's important to understand this concept of comma-separated value lists. So it's a CSV file. It's the VI curve for the resistor R1.csv, and oh, what's this? Oh no, it's okay. CSV, which stands for comma-separated values, and it's basically delimited text. Historically, only commas were used to separate fields from each other, but I can show you. Let's open the file. Let's see if it opens. Yes, it does. So that's the content of that's a pure text file. There's nothing, no special magic behind it. It's really pure text. So I'm using a standard text editor. On Windows, you could use Notepad++. It's very highly recommended. Here I'm using Notepad QQ, but you could use any. You could even open this in Word if you liked. Because it's just a text file. And you see here that this text is delimited with a semicolon in this case. So it's not a comma-separated list or comma-separated values, but semicolon-separated values. And I highly recommend to use semicolons instead of commas, because in some languages, like the German ones, the comma is used as a decimal separator instead of a dot. And that causes a lot of problems. But when you because when you have the comma as a decimal separator and the comma as additionally the comma as a field separator, you really don't know how the numbers are arranged. But where's the decimal separator and where's the field delimiter? So therefore, use semicolons as a field delimiter is highly recommended. Okay, so and this text logically consists of two columns. The first column, so the first row here, contains the column headers, and it's volt in volt. So sorry, the voltage in volt, or the potential in volt, and the current I in microamps. It's just text, so I can change it, right, if I want. Right, so I can change it. So obviously I measured the current in the lab with my multimeter in microamps. So I chose the amplification of the multimeter such that the range is microamperes. So first column is voltage, second column is current. And now you see the set of numbers, right? Each row now contains one measurement. It's the voltage and the associated current, and the voltage and the associated current. And you see, so when you subtract the header, this file basically contains 22 measurements. So we have 23 rows, including the header. So that means we have 22 individual measurements, right? So now let's analyze them in a spreadsheet program to see how they are aligned. And we must not forget to calculate the power as well. Good. So there are so many ways to do this. I'll show you just my way, how I would do it. So let me open the file. I take the one R1 CSV. So now this dialog pops up. So first of all, it asks me about the character set, so the character encoding. So what is the original character encoding? That also can be a problem when you have CSV files from European languages or from non-American languages. Or, yeah. So UTF-8 is a standard Unicode which works in this case. But you will see later that you sometimes have to change the character set to Latin or to some Windows code pages or to some ISO character sets and so on. So you see there are so many. because one encoding is not enough for all languages. So there are too many characters. So it's so there are several ways how to represent characters in files numerically. But Unicode is okay. Default English is the locale. Yeah, the locale is basically the definition of how you represent currencies, how you represent time, wall clock time, right? Do you say 10 o'clock in the morning, or do you say 10 a.m., or do you say 10 p.m., or 22 o'clock? Then the biggest pain in the neck is basically the different encodings for dates, because you sometimes cannot really distinguish whether month or day, whether month is first or day is first. And I highly recommend to use ISO 6946 time representation standards. But for now it's okay. I just use the default English one, since we don't have any time here encoded anyway. So then the separator options are, yes, it is separated with a semicolon, right? So you can say sometimes you have files which have a fixed format. Then it simply counts the number of characters here and tries to separate the fields. But here we have a separator, which is a semicolon. And you can see fixed width wouldn't work at all. If we say, okay, let's say for some reason we would say it's not separated by a semicolon. You see it would not be separable. Comma is not the right one, so we use the semicolon. Then detect scientific notation. That is the number format, right? Because sometimes when you say, we could for example write 90, right, 90, or we can say 9 times 10 to the power of 1. So in the scientific notation you would write 9e plus 1, and e means to the power of. So maybe let me switch to my desk. So you could write, let's say 90.0, or you can say 9.0 times 10 to the power of 1. And so to the power of 1, you cannot write this in a line of text. So what you then do is you write 9.0 e plus 1, or e1 or something. E means 10 to the power of, right? 9e1 would be 90, 9e0 is 9, 9e2 is 900. Okay, so that's what scientific notation means in the numbers. Okay, so let's import this now. I think all our settings are okay. And it works. Good. Okay, so to make life easier, so you see that the numbers are nicely readable when we use microampere. So for example, the largest value we have here is 1000 microampere, which is 1000 times 1 millionth. So 10 to the power of 3 times 10 to the power of -6, which would be a milliamp. So 10 to the power of -3. This is 10 to the power of 3. This is 10 to the power of -6. When you multiply them, the result would be 10 to the power of -3, which is a milli. This 1000 microamps is 1 milliamp. But for my calculations, and when we look at the power and so on, it might be more convenient to go to maybe milliamps instead, or even amps. So let's calculate the power first by just multiplying these two. Let's convert the current first of all in maybe in milliamps. So I want the current I now in milliamps. No, in amps, because I need it later anyway. Okay, so let me convert this to milliamps, to amps. Okay, to amps, which is I have to multiply this field times 1e6, right? 1e negative 6, sorry. Micro is 10 to the power of negative 6. It's microamp. Oops. So that's trivial. And then let's go down here. Okay, so now we have this in a decent ampere unit. And I will add the same voltage again. You may think that this is not necessary or maybe a bit stupid, but you will see later that this makes our life much easier when we create a plot. So I simply say this is equal to this field and select this number, and I double click here on the lower right corner, and then it autofills the rest. You see now the formatting here is not really nice. I would like to go for scientific notation because then it's much easier to read, right? This is very bad. So how many zeros do you have here? Very hard to read. What are you talking about? What is the order of magnitude? So, and I would maybe change both of them immediately. So I select one of the columns, I press Control, select the second one, and now I hope that I can format them. Format cells. By default, since you can put several different data types in such a spreadsheet cell, it's usually a very general format, right? But now I want to go either here for a fixed number format with a certain amount of decimal places, right? Even here you see that the different decimal places are varying, but I select the scientific notation. And I use the standard one, so you see here are different formats. This is more the engineering format code. You see it would look like this. That's the format template, but I like this one better for now because it's a bit easier to read. And let's use 3 decimal places. This is what I recommend also when you do calculations. Use at least 3 decimal places. Otherwise, you're running into rounding errors in your calculations too early, right? So please use at least 3 decimal places. Okay. Yeah, for the current it's okay. For the voltage, not really, because the numbers are varying between 0 and 10 volts, right? That's how we designed the experiment. We are changing the voltage of the voltage source. So maybe I change that again back to another format. So format cells, and I go to number, and I use a number with no, this is also very ugly. You see, this is the thousandths delimiter with a comma. That's very confusing. Don't use that. So I use the standard number with a dot as a decimal separator and no thousandths separator. And again, 3 decimal places. Okay. Ah, yeah, look, this is nicely readable, right? That's good. Okay, now I have the current first and the voltage second. And that's exactly what we want when we plot the graph, right? We want I to be on the x-axis and V to be on the y-axis. This is the reason why I basically swapped both columns with this trick by just, basically referencing to the first column. It's completely identical objects here. So when I change a number here, let's say I change this to 2, you would see that this also would automatically change to 2, because what I did is I used this is equal to, which is then a reference to this field. It's identical, right? It's not a copy, it's really identical. Good. So now let's calculate the power. The power, P, in watts. And the power here would be current in amperes times voltage in volts. And again, double click. And you see the numbers are relatively small. The maximum power here are 10 milliwatts. Yeah, we can go for a scientific notation, or we can go for this engineering notation. Let's use the engineering notation. Let's see what it does. So we use a scientific notation, but this one with 3 decimal places. Okay, let's see. Not really nice. Let's use another format. Let's use the standard scientific notation. How does that look like? Yeah, it's okay. So you see 10 to the power of negative 3. This is milli. So here that's the range of milliwatts, and this is 10 milliwatts, which is then 10 milliwatts. And here it's very small. Right, these are 10 microwatts, 100 microwatts. Yeah, okay. So that is really small. Okay, now let's draw. Now what you always should do is you should immediately save the file, but not as a CSV file anymore. You should save it as an OBS file or an XLS file, depending on the spreadsheet you are using. I really like LibreOffice because it's Libre, it's free. So let's save. No, I don't want to replace it, and I think I don't know how I can change it. Maybe I have to export it. Save as, maybe. Save as. Save. No, I don't want to replace it. But what happens? I assumed that it would ask me if I want to change the format. That's a bit crazy. No, so let me change this to, I don't know, new or something. Save. Now it's asking me. And again, I could now save it as a CSV file, but the CSV file is really pure data information. You cannot store any formatting information like, let's say you are using boldface characters or colors in the cells or a diagram. So you cannot store the diagram in a CSV file. Therefore, I use this ODF format, which is the standard format of LibreOffice Calc. So it's a calculator, the spreadsheet program from the LibreOffice Office suite. Okay, you see now it's now new ODS, and that now saves all what we are doing here when we add diagrams and so on. So now let's select the two adjacent columns I and V. So I do this by clicking on C, clicking and then pressing Control, clicking on D, and now here's a symbol for insert a chart. And now you have to choose the right chart type, which is really important. It's very crucial. Use XY scatter. Don't use lines or something or anything else, because otherwise you would not plot Y against X. This is only possible when you use these XY scatters. And as I told you, so it's basically a set of points we have. here you would basically connect these points with lines. And as I told you in one video before, you can do that as long as you know what you're doing, but it's not recommended because it's a lie. You don't know what's in between the points, right? It's your assumption. And then you should basically express yourself clearly and say, okay, assume that it's a line or something, or I can maybe for drawing purposes or to make it more clear, the drawn curve or so, you can do it, but you have to know what you're doing, right? Don't just click on it because you think it's fancy. So use the points. XY scatter points. Next. So the data range is now, that is the name of the spreadsheet. So you can have several sheets in one of these files. So this is one of the sheets, the only sheet in this case. That's the name of the sheet. And within this sheet, you have now a data range from $C1 to $D23. So that is from the cell C1 to D3. Let's check. I can click here and have a look at the data range. It's exactly this data range from cell C, so column C, row 1, to D, row 23. $C1, $D, $23. That means, and the dollar sign here means it's really fixed, it's not relative, it's the absolute coordinate cell reference. Good. Next, that was okay. So the X values and the Y values, so this is column C and column D, that's okay. So data range is okay, data series is okay. Next. So let's draw a title. What would it be? It's basically experimental VI curve, or VI data of unknown resistor, basically resistor R1, right? We don't know the value yet. Experimental VI data, so voltage current data of unknown resistor. Subtitles, we don't need that. So the x-axis is column C, that is current in ampere, and the y-axis is voltage in volt. So when we conducted the experiment, we preset the voltage and measured the current, but for the evaluation of the slope, it's easier if you swap them, because then the slope triangle, the slope of the slope triangle is then the resistance. Otherwise, it would be 1 over R, the reciprocal value. So display legend, no, because we already know what this curve is. Display grid, yes, along the y-axis, and so parallel to x-axis and y-axis, and finish. And look how nice the data is, right? It's a very nice data set here. Oop, I didn't want to do that. Control Z probably. Okay, it's like this. Very nice. So let's save. Control S. So now you could improve this a bit, right? You can change here the numerical format of the numbers given. You can increase the density of the grids. You can change the fonts. You can change the background color or whatever. What I would like to do is to limit this axis here. No, because maybe not. But when you for example double click on the values on the axis, the labels, you can really change them, the text orientation, but you can also change the scale, right? If I double click on one of the labels on the y-axis, on the voltage axis, it scales them automatically. That's done automatically because of the range of the values, right? But sometimes you want this to be not automatic, but manual. And let's say we go to 10. Okay, and major tick intervals maybe 1. Minor tick count is maybe, or a lot, let's say, I don't know, maybe it's too much, maybe 2 and 1 or so. Okay. So, and then the same here. Automatic, yeah, 0, but we can fix it to 0 as well. And this will be, let's say 0.01 or something like this, major intervals, that's okay, minor interval count, okay. It's like that. But I think we missed a point, didn't we? Yeah, so we have to change this again. Because when you make it too tight, you are cutting off points which are outside the plotting range. So let's go back to the initial range. It was okay. Good. Okay, so now let's model this. Right? You see here the density of the points were a bit higher, and if you look very closely, you see it's not a super perfect line, but it's extremely good already. So now let's add a model. And how do we do this? So I have to select the plotting area. So double click and activate here the data set, the series we want to analyze. Data points, right? Now you see it's selected. The data is visible here. Right click, insert a format data series, insert trend line. That's what they call it. Okay, so it's in this case a linear model. We want to determine a function y is m times x plus b, which is approximating these points optimally. So we use a linear model. The trend line name now is Ohm's law, because that is Ohm's law. Ohm states that current and voltage are proportional, but only if we force the intercept to be 0, which means that the y-axis or that the trend line runs through the origin of the coordinate system in this case. Show equation and show the r² value, which is a kind of index which tells you how good the fit basically is. That helps you to assess the quality of the fit. And the best fit would be 1. So when your fit really matches all the points precisely, then the r² would be 1. So the x name value is I, and the y variable name is v. I think that's it. Okay. And now you get here the formula, which is the format is a bit ugly. So I change here the zoom level a bit. You don't see this. Let me switch off the camera. So here is, I can change the zoom and zoom in to, let's say 120 or so. I don't know, a bit more, plus 120. And I want to change the format of these numbers here, right? They have ridiculously many decimal places. So let's see how we can make it. So equation for data series V, that's the name of the data series. So the data series is V dependent on I. And we can now change the number format and say it is a number or it is scientific. What would I use? Let's use a number. the standard one with 2 decimals. Yeah, 2 decimals is enough in this case. Yeah, it's okay. And okay. Okay. So you see, when the r squared is rounded to 2 decimals, it's 1. So this fit is almost perfect. It's slightly deviating from a perfect fit, but it's negligible. It's really, you can say this model is a perfect fit. And now you can see what the expression, the Ohm's law now is, right? Because we were asked, what is the independent variable? What is the dependent variable? What is the name of the y-axis, y value? What is the name of the x value? And I said the y value is v and the x value is I, and suddenly Ohm's law pops up. And now you can read from this equation here that the resistor has 9,994 ohms, which is almost 10 kilo ohms. So let's determine the error. So we would have our model and maybe R rated, right? So you are taking your, so when you have the resistors, there are typical values. There is no resistor you could buy with 9,994 ohms. That doesn't exist. You would buy a 10 kilo ohm resistor, a 10,000 ohm resistor. And they have deviations because of the production. They are never ever precise. Usually they have errors around 2%, 5% or so. You can have very precise resistors as well, but usually it's not necessary. They can have these small deviations, but you see that here the error is even less than 2%. Maybe that resistor I used is rated to an error of 2%. We can calculate this later. So the model gives us 9,994 ohms. And the rated value, okay, but I want a different format, but we can change this later, is 10,000. 10,000, yeah, okay. You see, it's taking the standard format which we gave to these columns here, but we can change it and say, okay, let's change the format. Format the cells, and which one? This one. I don't need 2 decimals in this case, maybe 1. And then I should draw it correctly, because then it's 61. So I choose the precise values, 61, and it's now rounded to 1 decimal. You see, in fact, the number is still 9,994.61, but because of my choice in displaying the values, where I said I just want to display 1 decimal, it rounds it to 0.6, right? Good. So what is the difference between let's say this is the truth, right? This is the truth. The truth is what we measure in the lab. Okay, what we haven't taken into account is the measurement errors with the voltmeters and the ampere meter, right? That's also something you have to take into account, and that's basically what is rated. So they sell you the resistor as a 10K resistor, but in fact you measured it and it's slightly less. So what's the difference between them? Let's say the difference. And now let's say it is the rated minus the truth. The truth is the reference. Okay? So it's a value of 5. And here again, I would probably use this format. Yeah, I should have more. So 5, so is this a large, so 5 ohms difference, is this large or not? No, it's not, because it's 5 out of approximately 10,000. So what we do now is we measure the relative error R and say D, this is equal to the relative error, let's say error, I call this error, baby. Let me call this error. Error, in fact, it is relative. It's a relative error. This is the, you can say this is the absolute error, right? This is, let's say, error absolute, the difference between the truth and the rated, and this is relative. Relative to what? Relative to the truth. So how bad is this 5 ohms difference related to the real value? And you see it's extremely small. And now let's convert this to percentage. And you don't have to calculate this, you don't have to multiply this by 100 or something. You can change simply the format of the cell and say, okay, format cells, I want this to be a percent, and I need probably a lot of decimal places because it is so small. No, 0.3 maybe, yeah. So you see the relative error between your measurement, your measured resistance compared to the rated resistance is 0.054%. That's negligible, right? So this is a 10K resistor you have in the lab. Okay, so this is how you can determine resistors or resistance. The value of a resistor is the resistance from many experimental samples you are taking. Okay, so now let's have a look at the power. I want to draw the power as the dependent variable. How do I do this? I could say I use the power is and the voltage is what I preset. In this case, I draw the diagram, the power against the voltage. So let's see how this looks like. Let's add a diagram. Again, X and Y, dots, go on, that's okay. Back, what's the bubble size? This is wrong. Cancel. So again, let me select voltage and power. Insert a scatter plot. Now that looks better. Data series is power in watts. This is okay. Title is power dissipated in the resistor R1. X-axis voltage, Y-axis power, and we calculated the product of voltage and current such that the result is watt. So we multiplied volts times ampere, and then the result is watt. So we are not taking any micro or milli orders of magnitude into account. Display grid, no legend, finish. Wow. So, and you see the power is not linear. It is a quadratic function. And why is this? So let's do some calculation. So we said that the power is the current times the voltage. Let's say, okay, we have in our case P is I times V. With V I mean the voltage drop across the resistor, the voltage difference between the two terminals. And I is the current running through it. And from Ohm's law we know that I is equal to voltage divided by resistance. So it follows that the power is equal to V divided by R, which is I, times V, which is V squared divided by R. And you see P is proportional to the voltage to the power of 2. And if we look at this curve here, that looks pretty much like a parabola, right? I don't know if we can fit a parabola. We can try. I'm not sure. I haven't tried it yet, if that's possible. I would insert a trend line. Can we exponential, basically a polynomial, second degree polynomial? Yes, okay. Force intercept 0. So second degree polynomial is a parabola. First degree polynomial is a straight line, and the 0th degree polynomial is a constant. Okay, show equation of course, show coefficient. X value again is in this case the voltage. The Y value in this case is the power P. Okay, that's new for me. Trend line name. Power model. Okay. Wow. Yeah. So if you look at these values first, right, the power is in the range of, let's say, 10 milliwatts, 10 to the power of negative 2 watts, right? Very, very small. You see this polynomial fit here has a quadratic component, but for some correction, it also subtracted here a linear component, but this linear component is negligible because the factor in front is 10 to the power of minus 6. It's very small. So 10 to the power of minus 6 compared to 10 to the power of negative 2 here is very small, so it's negligible. The factor here, if you look closely, maybe let's change this. The numbers again to scientific notation because that's much easier to read, and maybe some, I don't know, let's say 3 or so, okay? You see the fit again is super cool, almost is 1, nearly 1, and here you can see the value in front of the P is 1.002 times 10 to the power of negative 4. And that is 1 divided by R, right? If you look here, you see this is 1 divided by R. So P is 1 divided by R times V squared. And then we have this tiny little correction here, this linear correction, which we neglect. So it's 1 divided by R times V2. So let's check if we get the same modeled, or we should have at least a similar resistance value. Oop. Okay. So let's check from this value here. It's so R from polynomial, from parabola, right? It's a parabola. What is it? It is 1 divided by the factor we have here in front, 0.002 E negative 4 And okay, we are pretty close to the one we got here from the linear model. Okay, let's move it here. No, this is basically, that's a simulation. What happened if I add more, let's see if I add more decimals. Form a trend line. Trend line equation, delete position and size, data range. Now here. Okay, 4, 5. Okay. This is one divided by 1.00236 E negative 4. Okay. You see, we have a deviation here, but which is okay because we are basically using two different models. Okay. So that's what I wanted to show you about Ohm's law. You think it's easy. Yes, it is easy, but if you look at the details, it can get very complicated. So there is so much behind it. The reason, first of all, it's fantastic that in certain ranges, the voltage is proportional to the current, or the current is proportional to the voltage. The voltage difference, the potential difference, is in fact the potential energy difference. And this potential energy difference drives the current. And the current is limited by a resistor. And the energy of this current is then dissipated in the resistor. So the energy it loses has to go somewhere and is converted into heat in the resistor. But you can imagine that if the power is too high, then the resistor has to dissipate too much power, and then it would get too hot, and then it would get destroyed. And then, of course, you would leave the limits of the proportionality between V and I, because you would change the resistor. You would destroy it, or you would change its physical properties. So the voltage, the Ohm's law, only works in certain ranges. Let's say moderate power dissipation. Okay, it's an ideal model, but it's cool. Good. Thank you so much for watching.